Every so often, the official clocks that govern our global infrastructure do something strange. At exactly 23 hours, 59 minutes, and 59 seconds, they stop. The system holds for one extra tick, a 61st second, before turning over to midnight. This is a leap second, and it exists because of a conflict between our machines and our planet. The baseline for modern civil time is International Atomic Time, or TAI. It measures time by counting the exact unvarying electromagnetic vibrations of a cesium-133 atom. These racks at the U.S. Naval Observatory, along with dozens of others around the world, maintain this standard. They vibrate over 9.1 billion times per second, maintaining an engineered precision that does not waver. Earth, however, is not a perfect machine. As it spins in space, the gravitational pull of the moon and ocean tides cause it to wobble. Our planet stumbles and gradually slows down, making the physical day slightly longer than the mathematical one. Our highly engineered atomic clocks are incompatible with the physical dirt and rock we live on. We have to manually hack our own global timekeeping network to keep the two synchronized. To understand the root of this exact mathematical tension, we have to look at how humanity first measured the sky. Early human societies naturally tracked the passage of time by watching the moon. It was the most prominent, rapidly changing celestial body available, completing a highly visible cycle of phases every 29.5 days. A severe mathematical problem arises when you try to stack those lunar cycles into a year. 12 cycles of the moon only amount to about 354 days. The 354-day lunar calendar bar runs parallel to a 365-day solar calendar bar, falling 11 days short of Earth's actual orbit. Tracked over 3 years, this error rapidly compounds. The 11-day gap expands into a 33-day misalignment, shifting entire months out of their original seasons. Relying strictly on the moon guarantees that agricultural milestones quickly drift into the wrong weather patterns. Survival for early farming societies required a more reliable anchor. Ancient Egypt's entire agrarian economy depended on the Nile River. Anticipating its annual life-giving flood required exact seasonal precision that the moon could not provide. Look at this historical photograph showing the landscape at the very base of the pyramids swallowed by water. Predicting this exact deluge meant the difference between starvation and a massive harvest. To find a stable metronome, Egyptian priests abandoned lunar timekeeping and focused their attention on fixed points further out in the cosmos. They tracked the morning appearance of a specific, brilliant star. They observed that the heliacal rising of the dog star, Sirius, always aligned with the onset of the rising waters. Tethering their counting to this star allowed the Egyptians to create history's first purely solar civil calendar, locked at exactly 365 days. The true solar year is roughly 365.25 days long. Because the Egyptian calendar lacked leap years to account for that fraction, it drifted backward against the physical seasons by 1 day every 4 years. While this 365-day model provided the stability required to manage an empire, its strict mathematical rigidity meant the civil date was slowly decoupling from the true mechanics of the solar system. The Egyptians maintained a rigid calendar that drifted away from the actual position of the stars. Today, we maintain rigid atomic clocks that drift away from the actual position of the Earth. We currently track 2 competing masters. UT1 is an astronomical time standard based on the messy, fluctuating rotation of our planet. TAI is the unyielding, perfect time defined by the vibration of atoms. This chart maps the physical tension between the two systems. As the Earth's rotation slows down, the bottom timeline, tracking astronomical time, starts to lag, tearing away from the steady march of atomic time on the top timeline. To bridge this expanding gap, international timekeepers established Coordinated Universal Time, or UTC. It relies on the perfection of the atom, but legally accommodates the Earth's wobble. When the gap exceeds 0.9 seconds, the system inserts an extra leap second. This physical block shifts UTC backward, snapping it perfectly back into alignment with the planet's lagging rotation. We measure time with absolute quantum precision, yet we still have to reach into our own digital infrastructure and hold the clocks back, maintaining an ongoing compromise to keep our perfect math tethered to the same messy sky the ancient Egyptians watched.